Hello everyone, my name is Petit. I'm a postdoctoral researcher at McGill University, and I'll be presenting my paper on the MOAR Planner, which is a multi-objective and adaptive risk-aware path planning algorithm for infrastructure inspection with a UAV. This work was carried out during my previous postdoc at the University of Sherbrooke with the support of Professor Alexis Lucier-Desbiens. The algorithm was developed as part of a project for the autonomous inspection of high-voltage power lines using a drone. Hydro-Quebec and DroneVol designed the line drone to predict the remaining lifespan of conductors. It is equipped with a vertical lidar for conductor detection and non-destructive sensors for contact inspection. The challenges for trajectory planning during this type of drone inspection mission are typically related to real-time calculation, risk of damage and collision with infrastructure, battery management, and flight time optimization to capitalize on good weather conditions. Certain risks also arise and evolve over the course of a mission, including wind instabilities, loss of communication, localization faults, and reduced flight autonomy. Our aim is to plan inspection, exit, and evacuation path. When using the line drone, the solution search domain can be simplified to a 2D plane as it can roll along the line once it has landed. However, the rest of the algorithm remains generic and applicable to the 3D domain. Trajectories must optimize multiple objectives, namely safety, time, and energy, while adapting to the evolving risks during the missions, such as wind, communication, localization, and battery. The MOAR Planner provides adaptive solutions in space and time. Our algorithm offers precise control over mission objectives and safety considerations thanks to risk-aware cost adaptation function. We also enable real-time recalculation using pre-computed cost maps. We improve safety awareness near infrastructures by introducing damage and insertion cost concepts, and also an adaptive speed planning framework. And finally, we perform an exhaustive search for the optimal solution in a discretized graph using motion primitives. I'll detail all these contributions in the next few slides. First, the safety cost maps are pre-computed to support real-time recalculation, and the safety cost consists of three components, namely collision near obstacles, insertion into the structure, and damage in the event of a fall. Another cost map for speed is also pre-computed for better real-time computation. The drone will move faster in horizontal flight than in ascent for energy reasons, and it will move slowly close to obstacles for safety purposes. The state and action spaces are discretized using 9 motion primitives. States are thus represented in a 3-dimensional graph, including the direction of flight in the transverse dimension. The graph representation is flattened here to facilitate visualization. You can see a path example on the right, in which speeds are defined entirely by position and flight direction. The optimal path is then searched using A* or Dijkstra in the case of multi-goal planning, such as to exit and evacuation zones. The cost function integrates the safety cost, which is provided by pre-computed cost maps, and the time and energy costs that are computed using defined speeds. Finally, the cost coefficients are defined with dynamic adjustment functions. For example, a high wind risk will put more emphasis on safety, while a low battery risk will put more emphasis on time and energy. We tested our planner in 36 different scenarios for exit, inspection, and evacuation path in different environments. And in each scenario, we tested all possible combinations of cost coefficients. All these trajectories were compared with benchmark algorithms. There are similarities with A* and Dijkstra, which are close to our fastest trajectories, and other Voronoi-based trajectories, which are close to our safe trajectories. We also analyzed the same results with metrics such as path length and average obstacle clearance, and also others that you can find out more about in our paper and our video by scanning the QR code on the right. We show that our trajectories cover 150% of the benchmark trajectories in terms of path length and 75% in terms of optical clearance. Our results confirm that varying the coefficients facilitates a gradual transition among different desirable behaviors. With this in mind, we tested our modulation of the cost function with mission risks. We show the results of varying the wind risk on the left. We can see that our algorithm makes a gradual transition between A-star and Voronoi style behaviors while covering between 90 and 100% of this range. This range can also be increased to 150% if we use a steeper cost adjustment function. On the right, you can see examples of trajectories with different risk indices. These results confirm that we can cover the whole range occupied by the benchmark algorithms with a single unifying algorithm. We tested our planner during an actual flight around a test structure made of scaffolding. The drone successfully navigated a safe, low-energy trajectory while performing real-time recalculations. We also tested our navigation system on several power line infrastructure inspection missions in the field. We are currently finalizing our work on extending our planner to the 3D domain with a continuous trajectory representation, and we are also working on a more advanced energy consumption model, as well as the optimization of acceleration profiles for faster vehicles. You can test a simplified version of our algorithm online on my website if you scan the QR code on the right here. Thank you for listening.